just a powers chart that will, when we start in the actual numbering systems, should really help, and you'll be able to use this on test because this is something that if you dealt with years and years and years, it'd be no problem. But since you're learning this, then this chart you'll be able to. So we pretty much will know this, right? Everybody okay here? This is pretty. This is called positional rotation. We'll use this just to give you an idea of how we set this up and how numbers really go. So I know here in school you learn this as you learn this as units, you learn this as tens, you learn this as hundreds, and you learn this as thousands. That's the way they taught you, right? So you'd say 6,310, right? That's the way you learned it. But you got to understand all these other bases, you got to understand that a weighted numbering system, this means where each number actually holds a value toward the weight of the number, actually deals with these powers. So if I was to write this number in positional notation, it would look like this. So that would be 0 times 10 to the 0, right? This would be 1 times 10 to the first. This would be 3 times 10 squared, and this would be 6 times 10 to the third. That's what each weight actually holds. So it's actually the base raised to some power. And I can keep going. So 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, and supposedly it goes to infinity, but we don't know what infinity is. And now on the other side, it does on minuses, right? -1, -2, -3. And then we add them all together, we come up with the actual number. So 6 can be anywhere. The symbol that we use to represent a 6 could be anywhere in the number, but the actual value it holds to the number depends on its position within the number. So the fractional portion, we start off with 10 to the -1, 10 to the -8, 10 to the -1, 10 to the -2, 10 to the -3, and supposedly the minus numbers could go into infinity. So I guess that means they're in a circle, right? Since they both go to infinity, I don't know. And we write it in positional notation, and which gives you an idea of the weight of each number, right? Everybody understand that? Okay. Don't lose anybody. A real number have weights that are both positive and negative powers of tens. It has an integer portion and has a fractional portion. Everybody understand that? We call those what? Real numbers. So when we deal with numbers in the PLC, we're going to have to specify what it is, whether it's a real number or this next one. Real numbers, digit to the left of the decimal point represents the integer portion of the number. And what's the integer portion? Integer? Anybody know that term? That's the whole number portion. And then we have the fraction to the right of the radix point, or we call it a decimal point. So the technical term for that point that separates the integer from the fraction, the technical term is a radix point, but most people call it according to the base. So y'all learned it as the decimal point, right? We have what we call an integer. An integer is nothing but the whole number. Have weights that are positive powers of tens, numbers that can be, has no fractional component, can be positive or negative. Most PLCs establish what type of integer you're using. We can use an unsigned integer, or we can use a signed integer. So unsigned integers, these would be considered to be positive. Hey, Joseph? Okay. And then signed integers. This is going to tell us a lot about the range of the numbers. So 0 is an integer number, even though 0 technically has no weight, no matter where it's in the number. So two types of integers we have in PLCs. We have what we call an unsigned integer. These are always assumed positive. And then we have a signed integer, which could be either a positive number or negative number. And this is going to determine the range that's available to us. And we're going to have to learn that, guys. Number system, a writing system for expressing numbers. That is a mathematical notation representing number of a given set using digits or other symbols in a consistent manner. A number system used in PLC is decimal, a binary, octal, and hexadecimal. So, of course, everything in the PLC is binary, but binary is going to be, you'll learn right off the bat, it's really complicated for humans to understand. So when we enter numbers, we're going to have three options. We're going to have decimal, binary, octal, or hex, and we'll show y'all how we can designate what that number is when we enter it into the PLC. Are we okay? So binary, we're going to look at that. We even to understand the tables that we're going to look at inside the PLC. Fixed point number, numbers that has a fixed radix or decimal point and the number of digits move. Numbers where the fractional portion of the number is fixed. For example, money. So in the old days, and even you can used to. I hadn't done it in a long time, but you could set your number up for fixed point. In the old days, you could actually watch the cash register operator enter money, and they'd start typing, and it would actually the decimal point would be set, and they'd start entering numbers, and the numbers actually move around the decimal. So $11, I'd enter 1, and it would be over here at 0.01. Then I'd hit her 1 again. Then I'd enter 0, 0, and it'll move across. That's still used somewhere. Floating point numbers, numbers where the decimal point can be in any position in the number. Numbers where the fractional part of the numbers can vary. So fixed point numbers and decimal point numbers and floating point numbers. We need to kind of understand that, right? Everybody okay on that? Okay. So decimal number system. So we know a little bit about the decimal number system, and if we can compare what we know to something new, it makes it a lot easier to learn. So we know that the decimal number can consist of, if it's a real number, I don't need to put ones and zeros, guys. And this is what gets people confused, in that some of our numbering systems have used the same symbols. So if that decimal point can move, it would be a floating point number. If it's set, then it's going to be a fixed number, right? Everybody understand that? We know that each one of those has a weight of a power of 10. We know this is 10 to the 0, 10 to the first, 10 to the second, 10 to the third. But we got those in our head. We know without even thinking that 10 to the third is 1,000. We've dealt with this numbering system so long, right? This would be 10 to the -1, 10 to the -2. We know those because we deal with money all the time, right? This would be 10 to the -3, if y'all couldn't say. And we know, but in maths, in decimal system, we don't even see that anymore. We know the 9 has a weight of 1,000. I mean 9,000. We know that, right? Y'all understand this? Are we okay? Now, if we can understand this, if you understand this, you know any base. You can use any base. So if I had base 2, the only thing in base 2 is zeros and 1. Use exactly the same 1 and 0 that we use in the decimal number system. So we repeat these symbols a lot, right? And then I put a point, and I would come over that. Well, I know this holds the weight of 2 to the 0. I know 2 to the 0 is equal to 1. Any number raised to the 0 power is equal to 1. So I know that holds the weight of 0. I know this is 2 to the first, so I know the decimal equivalent of that is 2. This is 2 to the second. So that's 2 times 2. What's that? 4. If I come up with the decimal equivalent of the power is 2. This is 2 to the third is 8. Where am I at? 1, 2, 3, 4. This would be 2 to the fourth, which would be 16. This would be 2 to the fifth. This would be 32. This would be 2 to the sixth, which would be 64. Can you see how 2? So what does it go? It goes 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, right? Everybody okay? Okay. So what you do is just take the previous number and do what? Just double it. And when you look at your chart, you can see that. So I gave you the chart. If you look at powers of 2s, it just goes what? 1, 2, 4, 8, 16, 32, 64, right? 128, 256, 512, 1024, 2048. Right. Okay. And then over here, this would be minus. Well, all we do over here, this would be 1/10. This would be 1/100th. This would be 1/1000th. So all we do on the fractional portion is take what was on the positive portion and put it over 1. So this right here would be 1/2. This right here would half, Rich. This right here would be 1/4. This right here would be 1/8. Next one would be 1/16, 1/32, right? 1/64. So on the right-hand side of the fraction, you take the same powers that's on the positive and just put it 1 over. Base 8, 7356.34. This would be 8 to the 0. This would be 8 to the first, 8 to the second, 8 to the third. This would be 8 to the -1. This would be 8 to the -2. Base 16, 7356.34. This is the problem we have with base 8 and base 16 is that the digits are almost the same. So you gotta understand, your mind's going to interpret 7356.34. Your brain is going to interpret that as what? 7,356. It's not. It's a different base. It's a different number system. And this is something we're going to have to learn in computers because we know decimals so well. And when we see digits, what happens? Our brain actually interprets it as a decimal number, even though it might not be. So if this is base 16, this would be 16 to the 0, 16 to the first, 16 second, 16 to the third. This would be 16 to the -1, 16 to the -2. And I can make up a base. When I was in college, we made up a base 36. We used the 10 digits and then the characters. We use letters. So you can make up your own base. All you got to do is come up with that number of what? Symbols. That's all you got to do. So these are the ones. Binary. Of course, we're going to deal with decimal, thank goodness. But we got to understand binary. We got to understand octal and hexadecimal. These are the main number systems used on every PLC that I've ever dealt with. This semester, luckily, we're going to deal primarily with base 10. But if you take advanced PLCs or if you take PLC in automated systems, you're going to have to deal with these other bases. And you'll understand why we don't like binary. If we can do it in octal, it takes a lot less digits. Some processors in a computer PLC the processor in the PLC only understands binary numbers, period. So all our instructions, all our opcodes, and all our operands has to be in binary. We don't really understand that, right? Understand. All images displayed by a computer are a series of dots that are either on or off. So this is a series of dots. I'll go get my microscope and let y'all look at my display. Anybody know the prime colors that we use to display these? 4 of them. Just about every TV does that. Red, green, blue, and black. We turn them on, and I don't know if you came real close, you could see all these little tiny little dots in here. And then we group them So a group of those, we call them a triad. The black comes from the background. So the black is on a black background. So when your TV's off, what color do you see? Black. And then we have three colors: red, green, blue, red, green, and blue, and then black. And we can display all the colors that our eyes can see with those four prime colors, even though we say, I think we have six. So I can show y'all. I'll get my magnifying glass a little, and y'all can come up here one at a time. You can see the three little dots. We call those triads. And then we group them in squares that we call pixels. Have y'all heard of those terms, pixels? So that's a square that consists of a certain number of triads. So, and that's what you can do. You change what we call the resolution. You're changing the pixel resolution. All images by a computer are a series of dots that are either on or off. Computer programs can process binary code into the series of dots a computer uses to display images on the screen. This means a computer can display binary numbers, it can display decimal numbers, it can display hexadecimal numbers, because the computer interprets the dots that it needs to turn on, right? Y'all understand? So when I bring up my calculator, wherever it's at, I don't have it up anymore. By the way, Windows has a nice scientific calculator. It's really nice. Windows 10 is actually better. But right up here, I can come up here and I can display my programmer's calculator. And I can come up here and tell my computer to do math. So notice we pick up some stuff. So right now, this is hexadecimal. And so we have digits 0 through 9. And then we have letters, what? A, B, C, D, E, and F. We'll learn that. When I come up and pick it up, when I take it to binary, the only thing I got available now is what? 0 and 1. But it don't make a difference. So I can come up here and I can enter a large binary number. Is that big or little? Is that number really big or medium or small? We don't really know because we interpret it as decimal, right? So this would be that number displayed in octal. This would be the number displayed in hex. And this would be that's decimal, 363. But look how big it looks. So this is one problem we have with binary. It takes a lot of digits to represent numbers. So this is that number in hexadecimal. This is a number in decimal. This is a number in octal. This is a number in binary. And so all the computer is doing is it's looking at binary, but it takes that and says, okay, what dot pattern do I need to turn that on, right? You understand? So the only number system the computer actually understands is binary number system. So your Windows calculator, you can look at all these different bases that we'll be dealing with this this semester. Octal we don't use much anymore, but this was the first high-level numbering system that PLCs used to represent large binary numbers. So every PLC that I've dealt with for years, even brand new ones, still support these. The primary one, of course, is decimal, hex, and the binary. We'll get into those when we get into different functions. This means the computer can display binary numbers as binary, decimal, or hexadecimal, or octal. So number systems used by PLCs. So binary, decimal, we know that. We can look at the numbers. We know the weight. We don't even have to think about it because we've been dealing with the decimal number system ever since we were in kindergarten, right? Basically, introduction. Elementary school for sure. This is where so we've been dealing with this quite a few years. Binary only has two combinations. It's a base 2 number system, so the only thing we have is zeros and ones, which makes it nice as far as electronics goes. So think about the decimal number system. I'm trying to send you information using the decimal number system. So I'm up on the hill up there in front of a building, and I got a flashlight that has 10 light combinations on it. and I'm sending you numbers. How many of y'all would write it down right? Nobody, right? But how far could I get away and you tell if the light was on or off? As far as you could see me, you could tell if the light was what? On or off, even though it wasn't exactly the brightness all the time. So this is the advantage of binary, is that we can store it real easy, because we can store it as voltage levels, right? You understand, either 0 or 1. We can transmit it real easy, 0 and 1s, right? You understand, and we're not trying to interpret different levels. But the binary number system is very cumbersome because it's only got 2 combinations. So that means I can come over here and I can write down 100, and this is base 10. So what I'm going to do, guys, that could be binary, that could be decimal, that could be binary, that could be octal, that could be hexadecimal. So what I'm going to do is I'm going to put a little subscript to let you know what base that is. It's not raised to, but this would be the same number. So that would be base 2. Well, look, I can represent with 3 digits in base 10, right? You understand? It took what? It took 7 digits to represent it in base 2. So that's one of the problems we have with binary. It's very, very cumbersome. And this is why your computer has so much memory in it, is because we're dealing with a number of bits. And what's the processor size now? 64 bits? 64 bits. So that means our data bus has got to be 64 bits. Address bus is different. All the registers in the processor has got to be 64 bits. And we can deal with big numbers with 64 bits. Octal, we can have 7 combinations. So in octal, that same number would be equal to 64. 64. You shouldn't say 64. You should say 64, because it's not decimal. In hexadecimal, that number would be, it would be the same. It would be 64, guys. So we're not going to, I'll have to show y'all some advantages of that in a minute. A numbering system. So what we have to do in hexadecimal is we have to have, each digit has to have 16 combinations. So we use the first 10 that we get from the decimal numbering system, and then we switch to alphabet, A, B, C, D, E, and F. So in decimal, this would be 0 through 9. This would represent a decimal 10. This would represent a decimal 11, 12, 13, 14, and 15. So all we did when we did our base 26 is we just went all the way to Z with this, which gave us 36 combinations. So the problem we have is that I can have numbers that we think, so that number right there, how many 1 and 0, how many numbers could that represent? It could represent a lot of them, right? It could be what? It could be binary, it could be decimal, it could be octal, it could be hexadecimal. But each one of them would have a different weight depending once you convert it into the decimal number. Binary, used by computers and digital devices to electrically transmit, store, and process information. Easy to electronically transmit and be received accurately. Easy to electrically store for later use. Each of the electronic, it should be easy to electronically perform math and logic. Disadvantage, it requires a very large number of digits to represent decimal numbers in codes. So it's easier to store, it's easier to do math. The circuits that do math are a lot easier. It's easier to accurately store. So when you store something on your USB drive, on your thumb drive, it's all 1s and 0s. So all they're doing is basically storing voltage levels in there, right? So it's kind of like a little capacitor device. Octal, used by computers to represent large binary numbers with fewer digits. was the first high-level numbering system used by computers and PLCs to represent binary numbers and codes, still supported by most PLCs. Disadvantage is hard for most humans to understand because it uses the same digits as the decimal number system, and that's what our brain wants to see. Hexadecimal, used to represent large binary numbers and codes with fewer digits than decimal and octal. After decimal, the most widely used number systems used in computers to represent binary numbers and codes. And this is not used by the computer, this is used by us. Your computer only understands one number system, and that's binary. But it's so big and so inconvenient for us to do these binary numbers, it's almost real hard, especially the bigger the numbers, for us to comprehend them or even get them in the computer. Hard for most humans to understand. So a binary number system has a base, also called a radix of 2. Only 2 digits, ones and zeros, are represented. All binary numbers created from combinations of these 2 digits. So we have what we call the least significant bit. Everybody okay on the least significant bit? It's the digit to the far right, right? The most significant digit is the digit or the bit to the, and let's see if I do that. Let's get some terms out of the way. So first of all, we call these things. We have terms for these numbers. So anybody know what we call a group of? We call this a bit. Let me do this in a different color. So this is a bit. We call a group of 4. We call this a nibble. Y'all probably heard the next one, a group of 8. This is referred to as a byte. That's B-Y-T-E. And this is the way your memory's laid out. Memory's laid out in groups of bytes. And most people have lost that term. So most people say, how much memory do your computer in it? They'll say like 8 gigs. Well, it's actually 8 gigabytes. And so I hate that term gigs and teras. It's terabytes. So this is our fundamental storage inside the computer. So every 8-bit has its own address. And then what we do is we grab certain numbers of bytes to create these words. So a 64-bit would come up and grab what? 6 bytes of memory every time, or 6 addresses every time. We have a group of 16, and this varies between microprocessor. This is called a word. This is a group of 16. And then we have a double word. This is a group of 32. Then we have a quad word. This is a group of 64. And these down in here are a little different in microprocessors. In PLCs. And I'll give y'all a chart of the that tells you the actual names we give them in PLCs. So this would be a binary number. So this would be laid out in power. This is the integer. And guys, one of the labs you're going to do is a hand-in lab. And it's going to have fractions. And we're not going to deal with fractions that much. We'll look at them. But when you do the lab, if you convert the whole number, don't worry about the fraction. That'll be the answer. So you won't have to deal with the fraction, but I'll show you how to do the fractions. So each one of them holds a power of 2. So let's say I wanted to convert this to decimal. Well, what I would do is I'll come up here, and instead of me putting the weights of the powers of 2s, I'll put the decimal weight, the equivalent decimal weight. What's 2 to the 0? Any number raised to the 0 power is 1. 2 to the first, 2. 2 squared, And we just take double every time. What would that be? 8, 16, 32, 64, 128, 8, Rich. 256. Okay. Now, if I wanted to get the decimal equivalent, or what this decimal number this represents, all I have to do is write down the decimal equivalent that has ones in it. Because if I multiply 0 times 128, what's that? 0. So it don't have any weight. So I would say, to get the weight of this number, I'd say 256 plus 32 plus 16 plus 8 plus 2. And I add those numbers up. Y'all add them up. Y'all can use y'all's calculator if you want to, and tell me what the decimal equivalent of this number was. You can use the calculator. Everybody do it. You can use it on your phone. Everybody's got a calculator somewhere, right? Or add them up longhand. It's fine with me. That's a good way to do it too. I don't know. We'll see. I know it has a chance of being right. By the way, anytime you add an even number and an even number, it's always even. If you add an odd number, it's always even. So there's only one way we can get an odd number, and that's if we have this bit right here. If this bit right here is a 1, that means my answer should be odd. If it's a 0, my answer should be even. So this is the only one that'll make it odd, right? You understand that? So if I have a 0 right there and you convert it to decimal and you come up with an odd number, it means it's wrong. If you come up with an even number, it has a chance of being right. So that's the odd bit right there. That's the odd man out right there. It's just like on decimal. It's just like on a decimal numbering system. All those numbers to the left has nothing to do with whether it's even or odd. It's that last digit on the right that determines if it's even or odd, right? You understand? It's a little easier on the binary number system. 314, base 10. We okay? Everybody get that? Yes, no? So that's all we have to do. All we have to do is just, and you've got the powers of 2s all the way up to what? 2 to the 40th. On that handout right there. We won't deal with numbers that big, but even me trying to call this out to you, 1 0. So if that wasn't on the board, if I said 1 0 0 1 1 1 1 0 1 0, somebody in this class would make a mistake, right? But if I said 1 3 A, even though you don't understand it, everybody in the class would have got it right. And that's hexadecimal. But you see, I went from binary to hex without what? Not even thinking about it. And hopefully sooner or later you'll be able to do that. So how do we convert from binary to decimal? We develop a table using the decimal equivalent of each power of 2 from the right to left. Write the binary number in the table under each decimal number. Make sure the least significant bit is aligned with the least significant bit. Add the decimal equivalent that has ones in the binary number. So we just make a chart, just like I did. Start with what? For some reason, people want to start with 0, but we start with 1. And then we do what in the binary number system? We just do what every time? We just double it. Then what do? We write down the decimal equivalent for just the ones that's got 1 in it. Add them together, and then that'll give us our decimal equivalent. So look, 314 took 3 digits, but the binary number took a heck of a lot more, right? So this is the only problem we have with binary, since only each digit only has 2 combinations. It's going to take a real long thing of binary digits to represent decimal numbers. So what's that? 9 digits to represent the same number that I would in decimal. Are we okay? Okay, so let's convert this one right here. So should I expect an even answer or an odd answer? Odd. So if you come up and you get an odd answer, if you get an even answer, you know it's what? You know it's wrong. If you get an even answer, it don't mean it's right. It just has a what? It has a chance of being right. So guys, y'all do it. Oh, I need to put the base. Y'all remind me to do that. And this is the problem we have is that would be a legal octal number. That would be a legal decimal. If it was hex, that would be a huge number. Those combinations would be legal in decimal. It would be legal in octal. It would be legal in hexadecimal and binary. So anybody got it yet? Three oh one. 301. Everybody get 301? Somebody didn't get that? So just because you get an odd number don't mean it's right. It's just that it has it can be right. What we're working on now, there'll be powers of twos. So what we're doing now, we're going from binary to decimal. And why do we need to do that? Well, the binary number don't make any sense to us right now, right? To us, it looks like an extremely big number because it's got so many digits. I know our answer should be what? Even. $90. So what'd y'all get? $170. How did I miss it that much? Oh, I'm sorry. That's 1010. So 160, yeah, 170. I missed a bit. Are we okay? So how would we convert decimal to binary? So what we'll do is we'll come up with a decimal number. Let's say 300. Let's do a number we did over here. So we'll simply come up with the right one. So this one right here was 170. Okay. So what we'll do is we'll draw a chart listing the decimal equivalents of the powers of twos. We'll subtract the largest possible decimal equivalent of a power of 2 from the number being converted. We'll write a 1 in the bit position of the power of 2, subtracted. We'll repeat this until we reach 0. So I'd come up here and I would write down a chart. I go 1, 2, 4, 8, 16, 32, 64, 128, 256. I always like to go one pass to make sure I got enough digits. Now what we're doing is we're going from decimal to binary. So what I'm going to do is I'm going to take my decimal number and I'm going to subtract from it the highest decimal equivalent of a power of 2 I can. So what's the highest thing I can subtract from 170? Okay, so I'm going to put a 1 in 128 and I'm going to subtract 128 from it. And what does that leave us? What's that? 42. Can I subtract a 64 from 42? So I'll put a what here? Can I subtract a 32 from 42? So I'll put a 1 and I'll subtract 32. What does that leave me? 10, yeah. Can I subtract 16 from 10? No. Can I subtract 8 from 10? Yes. Put a 1, subtract 8. What does that leave me? The 2. Can I subtract a 4? Can I subtract a 2? Okay, so I put a 2, that leaves me a 0, then I just fill in the rest with 0. As soon as you get that 0, everything to the right gets a 0. So that would be the decimal equivalent. That would be, this is binary, this is decimal. So I usually go one pass to make sure I got enough digits. If you get this guy, if you get to this guy right here, and you still have something to subtract, what does that mean? You did something wrong, right? So we should subtract and get a 0 somewhere down this line. When I get that 0, we fill in everything else with 0. So let's do 275. Count in decimals. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we know how to count in decimal. This is counting in binary. 0, 1, 2, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. And this would be counting all the way up to 63, which gives us 64 combinations. So you can see right off the bat how much more efficient decimal is than binary. So binary is going to take a lot more digits to represent the same numbers, right? You understand that? But then it's got all those other advantages that makes them what we use in PLCs and what we use in computers. So let's say this is something you don't have to know how to do. But let's look if I was going to add in binary. So what's 1 plus 1? Huh? Well, what's 2? Well, 2 is this. So I'd say 0 with a carry of 1. So I'll write down the 2. Y'all see that? Then what would this be? 1 plus 1 would be what? 0 with a carry of 1. So we carry on 2. 1 plus 1 would be what? So I'll write down a binary 3, but I put the carry up here. What would be 1 plus 1? 0 with a carry of 1, 1, 1, 0 with a carry of 1, and I just added those numbers. It's not 10. You see it as 10. So what is this? That's what your brain sees that is. But this is base 2. So this would be 1, right? This would be 2. So that's 2. 1 plus this is 2. So that's a 2. But our brain sees it as a what? A 10. Our brain sees this as a what? 11, but it's not. It's a 3. In base 2, that's a 3. So this would be 1 2. So that's 1. We got a 1, so we'd add 2, and 1 that'd give us a 3. And that's the problem is we see the number as a what? As a base 10 number. Because why? So I come up here, I said 1 plus 1 is 2. So I'm going to write down a 2, but my carry is there. It's just like in base 10. So if I said 53 plus 67, well, that's 10, so I write my 10, but I write it like that. That makes sense? So, and that's the problem we have. We automatically, our brain sees 10 as a what? As a 10. So I'm not writing down a 10, I'm writing down a 2. So this would be 10. So that means I carry a what? I carry a 1. So that's what we're doing. So all I'm doing is writing down 10. So if I had 56 and 97, I'd write down 13, right? But the carry goes up next. Well, this is the same thing. So this is 2. 1 plus 1 is 2. That's going to be 0 with a carry 1. 1 plus 1 plus 1 is 3. So there's my 3 right there, right? Then 1 plus 1 is 0. 1 plus 0, 0, 1, 1, 0, 2. We just write it out on the next one. So it's exactly the same feature, but I don't have to know that 7 plus 3 is 10 because my only 2 answers are going to be what? It's going to be 0, 2, except when we have very, very large numbers. Okay, so let's see how we would subtract. So let's subtract these numbers. So in decimal, we borrow a 10, right? So in binary, we're going to borrow a what? So in decimal, when we borrow a 10. In binary, we're going to borrow a base 10, base 10, base 2, base 2. In binary, so in base 10, we borrow a 10. In base 2, we're going to borrow a 2. So this would be 1 minus 1 is what? Okay. 1, 0, 0, 0, 0. Oh my goodness, what am I going to borrow? I'm going to borrow a 2. You borrow the base. 2 minus 1 is 1, and that would be the answer. So in base 10, you borrow a 10. In base 2, you borrow a 2. Yeah, but I borrowed from that. I'm sorry. I didn't mark it out. Sorry. So when I marked this out, it made it a what? 0. So that's binary subtraction. Once you learn the basic techniques, and the rules in base 2 is exactly the same as the rules in base 10, except here we're dealing with base 2. So, right, you'll understand. So over here we're carrying 2s. Over here we borrow 2. So in base 10 you borrow a 10, right, from the next higher power. In base 2 we borrow 2s. Now we deal in multiplication. It gets a little harder. So multiplication. So what's 1 times 1? What's this? 0. What's this? Wait a second. I'm doing it wrong, guys. Don't let me get by with that. So we start over here. We multiply this, right? So basically what you do, if you see a 1, you just write, so 1 times 1, then we go to here, then we multiply it by that, then we multiply that, then we multiply that. So what I basically do is just do what? Write down the number. Are we going to have to know how to do this? No. But I just want you to see how easy it would be for a computer. When we first, the first microprocessors we had, they couldn't do, the only thing they could do was add and subtract. That was the 2 math instruction that the first processor that I dealt with, that's the only thing they could do was add and subtract. So to get multiplication, to get division, you had to write a program to do that. Now our computers do that for us. So this would be 1, 1, 1, 0, 1. And then I would come through and multiply by this. So that would be what? 0, 0, 0, 0, 0. Of course, back in school, you learned you could shift over twice, right, for every 0. And then I would say this would be 1, 1, 1, 0, 1. And then this would be 0, 0, 0, 0, 0. And this right here would be 1, 1, 1, 0, 1. And then what would I do? Huh? I would add them, right? So this would be a 1, this would be a 1, this would be a 0, carry a 1, this would be a 0, carry a 1. This would be a carry of 1, that would be a carry of 1, so this would be 0 with a carry of 2 1s. This would be 3, right? So it'd be a 1 carried with 2 1s. And then this right here would be 4. So it'd be a 0 carried with 2 1s. That'd be 1 with a carry of 1. That'd be 0 1. So what you do on this one is you carry a 1 every time you have 2 1s. So you just count the number. And that's multiplication. Division is a lot easier. So let's divide. So would this go into this? So would 1 1 0 go into 1? So we'd move over. Would 1 1 0 go into 1 1? No. Would 1 1 0 go into 1 1 0? How many times would it go? If you say it goes 2 times, you got a problem, right? So then I would write it down. 1 1 0. Then I would subtract, right? So 1 1 0, and then I would bring down a 0. How many times would that go into this? 0, right? Then I'd bring down another 0. How many times would this go into that? 0, and that would be the answer. So whether you understand it or not, the circuitry that does the math is very, very simple, because all it's dealing with is what? Zeros and ones. It's not trying to carry a 3. It's not trying to carry this. It's just very, very simple. So what we did is we just looped it. So we would add this to itself that many times. And that's the way the first multiplication we learned that. So we've already talked about this. What's a bit? What's a nibble? A byte? Though, right? And y'all probably heard of this. Y'all probably heard of bytes, but a lot of people don't understand what that is. And unfortunately, that term is since the memory on everything is laid out in bytes, everybody's forgot that, and we call it gigs now, right? I got gigs. So our file server over there has 6 terabytes worth of storage. Word. So what's a word? This is a group of 16 bits. Double words. In PLCs, they refer to this as a long word. In computers, we call it a double word. PLCs, we refer to this as a long word. This is a group of 32 binary bits, starting from the least significant bit. In computers, we call it a quad word. In PLCs, we call it a double long word. And this is usually where PLCs give up right here, because a 64-bit number would have 2 to the 64th combinations unsigned. So 2 raised to the 64th would be that number right there. So past this double long word in PLCs, there's really no need to keep up with numbers bigger than that. If it was signed, we would have this many negative combinations, and we'll look at that later on. So that's a huge, huge number that basically exceeds anything that we can possibly even think about, right? You understand? So processors usually give up on 64 bits. These are 64-bit processors in here. but we can string quad words together if the application is written right. So that's a huge number. So in PLCs, it's a little different. So we use the same terminology all the way up to here. So word is 16 bits. A double word is 32 bits, but in PLCs refer to this as a long word. In computers, we call a 64-bit a quad word. In PLCs, they call it a double long word. So why they jump ship here, I don't have the slightest idea. But, so you specify that. You specify what base you're using, how long the word is. In these, we have very limited power with the size of our words. In your new PLCs, though, you can go all the way up to here. Hexadecimal, this is probably as far as say hexadecimal is used in medium and to large programmable logic controllers. Often people call it hex, which is not technically correct, but you'll hear that all the time. Used to display the PLC's memory map and to carry out math instructions created by grouping 4 binary bits. Hexadecimal numbers use base 16 and requires 16 digits. So this, what we use hexadecimal for is for the computer to display or you to enter very large binary numbers. And we can actually see this in PLC. So what's our digits? Our digits are what? 0 through 9, and then it goes what? A, B, C, D, E, and F. So this is the addresses. So these are binary addresses. But you can see A0. I'm looking for another one. 3C, 2C. Well, what they're trying to do, they're trying to give us binary numbers, but they're not using binary, they're using hexadecimal. This really comes into play if we start looking at the memory map. So this memory right here, this is the chipset PCI Express F04000000 through F08FFFF. That is a binary number, but my computer is not displaying it in binary, it's just displaying it in a number system called hexadecimal. Because it's a lot easier, it takes a lot fewer digits. And we can go between these bases extremely easy. So now, if I understand this, everything in the computer is assigned an address. And those addresses are binary. And this is all the addresses that's assigned in this computer right here. So far it goes up to DF9FFFF. And this is something on the system board. There's your graphics card right there. That's the memory in your graphics card. That's the memory in your audio circuit. The chipset that's actually running the motherboard. So these are addresses. And instead of it trying to give you that address in decimal, which would be big, and then we'd have to convert it to binary anyway, they give it to you in what we call the hexadecimal numbers. So this guy here, this in octal, like I said, PLCs use octal. These computers have given up on octal a long time ago. And I don't think you can see, you can't see the address and map on your computer, but it's still available with your computer. And what's it called? System information. So normally you have to search for it now. It's not in control panel. So this is the hexadecimal numbering system. So this is the decimal equivalent. This is the binary representation of each hex digit, and this is what the hex number would look like right here. So, you know, I can come up here and do this, 1695, and I can put base 16 out there, and everybody wants to see that as a decimal number. If I come up here and I put 1CB3, then most people say, oh, that's hex, right? So we have a big problem in our brain seeing a number and translating it as decimal. So this is important right here, knowing these patterns. Of course, this is important, and knowing the decimal weight that each of these digits represent. So normally, we look at, the book teaches how to go between hex and go between decimal and binary, but it does it using that division technique. And you have to have a calculator. Guys, if you have to have a calculator to do a conversion, you might as well get a calculator that does the conversion for you. So 1965, so Windows calculator. So the scientific calculators that I buy, I make sure, where's my calculator at? It has the ability to convert bases. So Windows calculator, you do what? You'd go to View, switch it over to Programmer's Calculator, and this brings up your bases. So I'm gonna do this in hexadecimal, and then I'm gonna come up and I'm gonna say 1695, and I got it in hexadecimal. This is what that would represent in decimal. So you can see right off the bat, hexadecimal is more efficient than decimal. So efficiency, we mean the number is smaller than its equivalent. So 1695 would represent that number in decimal. This would be an octal, so you can see it's more efficient than, decimal is more efficient than octal, so the number looks bigger, but it's got the same digits, right? And then this would be the number in binary. So which would be easier for, if I wanted to give you a binary number, what would be best? Would I come up here and say 5,782? Well, no, because now you're going to have to convert it over to binary, right? You understand? Would it be octal? Would it be 1325225? Or would it be binary? Which would be the most efficient way for me to give you that number? It would be hexadecimal. Okay. But I want you to look at this. I'm going to take that hexadecimal number and I'm going to convert this to binary in my head. Okay, that's base 2. Now, I did that without even what? Okay. Now, I can use a calculator. So, to me, a calculator would be a waste of time. Of course, it's going to drop the zeros. Okay. So, just start there. 10110 10110100100101. I can go this one right here. So I'm going to say did I kill my calculator? I think I did. Where am I at right there? Okay, so we'll take that number, 1CB2. I'm going to let my calculator do it for me. So I'm going to put it in hex. I'm going to say 1CB2. and I'm going to convert that over to binary. So you drop these 3 zeros, 1 1 1 0 0 1 0 1 1 0 0 1 0. How fast did I go to? So it took me longer to do what? Use my calculator. So there's got to be a trick to this. And there is no way in the world I could do what? I could go that unless there was something going on. Right? I mean, I could take any hex number. I could take those big old numbers over there and I could convert it to binary just like that. And it's not a trick. It's just that if you understand numbering systems, you understand what I'm doing. So we can calculate the number of combinations. I know it's almost time to go, guys. I can calculate the number of combinations that's available with a numbering system depending on the digits. So what's the biggest number? Well, how many combinations do I have with 2 digits of base 10? Well, I can say 10 raised to 2. That would give me 100 combinations. And what are those combinations? 0 through what? 0 through 99. So I can calculate the number of combinations, and you can calculate the biggest number, by the way, by taking the base raised to the number of digits minus 1. That gives you the biggest number you can represent, but the number of combinations. Well, how many combinations can I represent with each digit of base 16? Right? So that'd be 16 to the first. I got exactly 16 combinations. How many combinations can I represent with 4 bits of binary to the fourth? I can represent exactly 16 combinations. What do you notice? Each digit of decimal has 16 combinations. 4 bits of binary has 16 combinations. So what that means is I can use 4 bits of binary to represent each hex digit. So all you have to do to go between binary and hexadecimal is memorize that chart right there. And this is a lot easier than when you was in elementary school, you had to do your multiplication table. Multiplication tables is repetitive addition, right? So 5 times 3 is actually 5 times 5 times 5. But instead of you adding 5 to itself 3 times, you learn that 3 times 5 is equal to 15. So you memorize those multiplication tables. So now you don't have to add them the number of times. You just know what 5 times 3 is. Well, if I can, this is 16 patterns you have to memorize. If you get these 16 patterns memorized, then you can go between any base, any hex number and any. So let's do this. So let's say, what hex numbers do I want to take to binary? And I can plug it into the calculator. So let's say C3B9. Base 16. Well, what's the code? So C would be 1100. 3 would be what? 0011. B would be 1011, and 9 would be 1010. That'd be base 2. So I'm gonna come over here and bring up this calculator that I paid a lot of money for, and I'm gonna say, okay, I want to come over here. I'm gonna put it in hex, and I'm gonna go C hex C3 B9, and then I'm going to convert it to binary. It's already done it down here, by the way. And what do you notice? They're exactly the same. But it took me longer to use a calculator than it would what? And we can do it the other way. Let's say I got a binary number that I want to tell you. So I call this binary number out to you. I go 1100001110111001. How many of y'all have written that down and got it right? Probably nobody. Okay. So let's say I come over here and I want to convert this over to hexadecimal. What I'm going to do is I'm going to start with the least significant bit, and I'm going to set it off in groups of 4s. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then what I would do is I would write down the hexadecimal equivalent for each one of those patterns. So what's that pattern right there? That's a pattern for a C. That's a pattern for a 3. That's a pattern for a B. That's a pattern for a 9. And what I did is I just went from binary to hex. And you could have a weird number. I mean, you could come over here. It might not have exactly groups of 4s. So what I would do, I would still start over here, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, and I would pretend there's what? I would pretend there's 3 zeros up there. So that'd be what? 1, 6, A, and I've converted that binary number over to hexadecimal. This is what we're going to do with octal too. So the advantage of binary, of hex, is not going from decimal to binary. It's not going that way, right? It's not dividing by 16 and keeping up with the remainder. If I was going to go from decimal to hexadecimal, I'd go through binary. I'd convert it to binary first. I'd set it up in groups of 4s, and then I would convert it to hex. The only way you're going to do from hex and to decimal is that you'll divide by 16. But when you divide by 16, if you got a remainder, you got to figure out what the whole number is. So you have to multiply by 16 to get your whole number. So dividing by 16, the way the book teaches, to go from decimal to hexadecimal, dividing by 16, right? You understand? I wouldn't do that. I'd set up my chart. I would do what? I would go to binary, and then I'd set it up in groups of 2s, and that way I don't have to use a calculator. If you can go from base 10 to base 16 without a calculator, using the method they teach in the book, more power to you. But hexadecimal to binary and binary to hexadecimal, we can do that without a calculator. But all you got to do is learn what? 16 patterns. That's a lot better than what you had to do in elementary school when you was just a runt, right? You understand? Learning those multiplication tables. How far did y'all go up to? Y'all remember? 20th? That's more than I went through. So, but you memorize those, and what did that help you do? It helped you, instead of adding 5 times 5, instead of adding 5 times 5 to itself 5 times, you learned that 5 times 5 is 25. You memorized those tables. It maybe took flashcards. But if you want to be able to go between hex and binary and hex, then you need to know what? You need to know this, the actual hex digit, and you need to know these patterns. If you know those, you can go between a binary and hex without even thinking about it, just because you meant. So, am I extremely No, I just know these 16 patterns, right? You understand? I got those in my head. So now I can go between any hex number. I can go back and forth without even thinking about it. So we're not ready for the worksheet. We should finish this up. And then we might try to play around with the PLC a little bit on Wednesday. We'll figure out where we're going to set them up. And I'm gonna have to get the software installed, by the way. All right, guys, any questions? So let me remember where I'm at.